requires a different level of organization. What I'm going to try to do is just do all the board work first, because we can't flip back and forth, there's very little space. And I'll do all my board work, and then if I have things to show, and I'm going to try to minimize that more and more because this is a big hassle. But today, I plan to show you some real data. Then I'll show you that stuff at the end. So, and then on that part, I will try to write down what we plan to do today and any other announcements. It kind of breaks it up nicely. So let's see. Today, what I want to do is pick up on where we have left off. So we have done quite a lot of work on getting these optical response and getting the response as a function of frequency for the conductivity. We know how to get the dielectric function, and from that the reflectivity. So we've gone through that discussion. Does anyone have any questions? Okay. That's something you should update. You all sent me your slides. Based on the discussions we had, you should update that and then submit it tomorrow. That's on the board, one of the... Okay. And so what I want to now do is, if you remember, I showed you some historical, this like Charybdis cup from the Egyptian days. And we posed the problem that way, that it had a certain color, and that color was coming from nano gold particles. And then we left that and marched into this big discussion of epsilon, omega, and so on. And now I want to come back. We have all the ammunition now, or almost all, to come back and address the issue of how these colors are coming at the nanoparticle level. So let me do that. Before I get into color, I want to just get a few numbers here. So visible light. Essentially has a lambda of 500 nanometers. Again, I want to convert it into EV because that will come into some of the energy scale. So if I just get E visible light, so let me just say this is for yellow. So E yellow is on the order of basically HC over lambda, and that turns out to be, if you put in all these numbers here, it will turn out to be, it's actually very nice, you can just see that. So let me just do it once. 15 eV second, C is 3 times 10 to the 8 meters per second, and lambda is 5 times 10 to the minus 7 meters. And so you see nicely all the powers cancel out, and what you get is just these bunches of numbers, which gives you 2.5 eV. So that's something to remember, that visible light is about 2.5 eV. Now, coming to our plasma frequency, which we talked about, let's get that scale. So, or another way to think about is that 1 eV is on the order of 1200 nanometers. So whatever way you want to remember. These are things to keep in mind. Okay, now let's look at plasma frequency. Get a number for that. So plasma frequency, A&M has a nice table, and essentially for gold, so for simple metals, it is of this form, 11.4 RS over A0 minus 3 halves times 10 to the 15 hertz. Okay, and for RS over A0, This is, if you remember, RS is the mean distance between electrons. It's dependent on the density, cube root. And for gold, this is a number which is like 3.01. So now you can see I have to, for once, I can't just do my order one all the time, because these numbers become a little important. So for the first time I had to go back and really put the numbers in. But otherwise this is a number of order 1, but that 3 will become important. Because as you saw, all these big powers cancelled, and it was finally the little 3s and 5s which gave us the 2.5. Okay, so if I take this, put it all in, and I won't waste your time with that, then E plasma turns out to be 9.1 eV. So just to be sure everyone is on the same page, what we are trying to address is that prehistoric or whatever, this Egyptian cup, where there was absorption by gold particles at a frequency of about 500 nanometers. Okay? So at about this thing. And I will show you the data again when I can pull down my slides. So the cup, so these absorption, when it was tested, had a frequency of around 500 nanometers. Now we want to see where is this frequency coming from. Okay, so here we have gold. We have treated gold as a free electron gas. That free electron gas essentially oscillates at a plasma frequency and gives us an energy of 9.1 electron volt, not 2.5. Okay? Is everybody with me on the same page? So we know what we are, because some of you have written, I don't understand anything in class. That really worries me. Because more than this, I cannot ask you to talk in class. And you have to take the initiative and talk. And if you still don't understand, you have to come to my room and shake me and say, I'm not understanding. But I don't care. I don't want to hear that. I absolutely want everyone to understand. And you must find your way to understand things. Because I think I'm opening all the channels at this point. So please ask me if you're following, if you're not on this page right now. It's okay? Okay, so the puzzle is this. If we treat gold as a free electron gas, and we say this gas is, of course, a free electron gas in a positive background, we shake it with an electric field, it has a natural oscillation frequency, it turns out to be so many eV. That's a very high energy scale compared to what would be visible. Okay, so clearly we need to understand that discrepancy.
But do we expect that if we could send light in at 9.1 eV, the gold would absorb at that frequency because this plasma would absorb energy?
Yes, the plasma would absorb energy. Okay. Except the differences are a couple of things I'm going to bring up. If it was an infinite slab of gold, it would absorb at that frequency. Absolutely.
Okay.
Now what we have to bring in are a couple of steps between this and the actual experiment. One is the fact, so these are the things. One is that it is a gold sphere. So we want to understand what does making gold from a big bulk into a sphere do to the plasma oscillation. That's one step. And then the second step is that the gold nanoparticles are embedded in a dielectric. So that's the next step. So we have the gold sphere, and the second, so this would be, let me write down here, bulk plasma oscillations. And so absolutely, if you were to just measure epsilon of omega for gold, right, it will have some structure of this kind. Okay? This is for gold. It will start out like this, and we will come back to this picture. I will show you this. You will get at about 2 eV. I'm going to show you some data for that. There will be some interband transition. So I'm giving you some of these answers before discussing it. Interband transition. And I'm going to discuss this in more detail. But then at about 9 eV here, this is omega. So let's say h bar omega here. We have the plasma frequency. And that is defined by that frequency at which epsilon goes to 0. Okay? And the form above that here, epsilon of omega then becomes 1 minus omega p squared over omega squared. Okay? So the part that this model treats, it does not describe any of the interband stuff. It is just a free electron gas. So it's basically describing this part of the physics, and it says in bulk it would have absorbed at about 9 eV. Okay? Now the first thing that we have to bring in is what happens if it's a sphere. So the picture is a bit like this, that now I have to look at a sphere, or it could be any other shape, like an oblate shape. But again, I have a plane wave coming from here. This is my E0, e to the minus I omega t, E of t. And it puts this gold into oscillation, and it makes, it separates again the charges, and you get more or less, let's say, excess negative charge here, positive charge here, displaces the sphere, sets it into oscillation, and that gives a plasma oscillation. So omega surface, it's called like a surface plasma. And for a sphere, this comes out to be omega p over square root of 3. I'm not doing the derivation, it's just doing E&M with a different boundary condition. It is a problem in Ashcroft and Mermin, chapter 1, problem 5. So you get the 3, square root of 3 for a sphere, and so the frequency is reduced, and that basically says that E surface plasma for a gold sphere would be about 9 eV over over square root of 3. That's 1.73, and that's about 5 eV. Okay, so still not the full story.
Does this require some dimensions of this sphere? I mean,
That's very important, yeah. So what it requires is that this dimension is d, let's say. D must be much less than lambda. Okay, so your wavelength of light is much bigger than lambda, and these are nanodots. So the dots are about 10 nanometers. Lambda is, let's say, 500 nanometers. We're very well satisfying that. And the reason for that, why is this condition coming in? It's coming in because we are trying to treat everything as a dielectric function. The dielectric function is a coarse-grained concept. You know, you're trying to take some medium and you're saying, well, on average, this is what it looks like. So you're averaging the properties of that material on the scale of lambda. So that's where this restriction comes in. Okay, so the next step is second step is to remember that, well, it's not only a gold sphere, but these nanoparticles are embedded in some medium. You know, there's some dielectric medium. You know, these were ceramic vases that were made, and so there's some ceramic dielectric function in which these dots are embedded. So you have some dielectric with teeny dots here. So this is the gold dot. And this is the dielectric. Do you have a chair, Tom? Yeah, there is one.
Sit on the cabinet.
You can take that.
Oh, thanks.
Rick on the other hand.
Yeah, there's chairs out there. You should grab one.
Okay. So that's the dielectric. Okay, so now again, basically what one can show is that the way to treat this is you have an external electric field, the medium produces some polarization, and then you get a net electric field, which is a combination of the external and the polarization. So I'm again going to skip that because it's taking us, this thing is growing into a whole research project of its own. And the person who's an expert on that in our department is David Strout, who spent years looking at different shapes of particles and so on. So I'm going to give you like enough of an idea, so if you get consumed by this topic and you want to learn more about it, you can go to him. But at least this way you have an overall picture of all the elements that go into such a calculation. So now we want to get, so there is an external field. So E0 is the external electric field. And P is the polarization of this composite object. And what that gives you is E local, which is the sum of these two, or the difference depending on how you put the sign. But E local turns out to be 3 epsilon naught. So this is a dielectric with epsilon naught over this epsilon of omega plus 2 epsilon naught, E0. Okay, this is something that comes from effective medium theory. Again, using the fact that my wavelength is much bigger than the size of these particles, I can define it as some effective medium, and using that you can get this. It comes with different names. It's often called Clausius-Massorti or Maxwell-Garnett, the lady I mentioned whose work was overlooked, Mrs. Maxwell-Garnett. Those are the kinds of theories that basically give you this kind of a result. Yeah, question?
You pointed at the limiting form of epsilon of omega as using that down there?
Yeah. So, no.
How is that going to explain the energy region of interest?
So I'm just going step by step. Suppose everything is within the plasma context. Okay? So within the plasma context, I have just treated gold as a free particle.
Mm-hmm.
And then I got this result, gold as a sphere but still free.
Mm-hmm.
This one, gold as sphere, still treated as this epsilon. I mean, this is a general expression. You could stick in here a better approximation, the best approximation for epsilon of omega for gold.
Sure.
Now, if I use this, then we'll see what we get. And it will not completely answer that story. So then we will know what is missing are these interband transitions.
Right, okay.
So let me actually, so long as you guys remember that, or let me keep that. Okay, now if epsilon omega is approximated, epsilon omega for gold, so this stuff here is for gold. So if epsilon omega for gold is approximated as 1 minus omega p square over omega square, then you'll get a denominator. You stick it all in, and you'll get some denominator. And I will get something like this. E local is going to be 3 epsilon naught omega square over then again defined by setting the denominator equal to 0, so we get omega squared equal to omega p squared I can take the square root. This is for gold dot in dielectric. Okay, and if you put in some numbers here, so if you put in some numbers, you get epsilon naught approximately 10. That gives you h bar omega surface plasmon, with the dielectric and all of that, approximately 2 eV. Okay, it's about 600 nanometers, which is close. Okay.
A small question about your notation. So you were calling epsilon naught the dielectric constant, not the dielectric constant of vacuum.
I kind of switch between these two, just because there are no more symbols left. So so there is a permittivity of free space.
Yes.
Okay, and that is the number that has all the dimensions with the farads and all that. That is what we call epsilon naught.
Right.
Now, whenever I say something like dielectric constant epsilon 0 is about 10, what I really mean, and I'm a little sloppy about it because at some level now, what I mean is this, that if I took my dielectric, whatever it is made of, silicon or silicon oxide, and I looked at epsilon of omega, right, at omega equal to 0. So this epsilon 0 is the epsilon of omega equal to tending, or equal to 0, let's say, equal to 0 of the insulator.
Okay.
And that is what I'm defining, and that number is what I'm calling epsilon 0 times permittivity of free space. And I need another symbol for that. That's what we were calling epsilon 0 of free space. So I have kind of taken that free space permittivity to be 1. Those are my units, and that is what I was calling this. So if you don't like that, what you could replace epsilon 0 by is this thing. It's the dielectric constant of the insulator at 0 frequency.
So it seems like we're mixing all sorts of regimes. We're saying, I'm going to use the 0 frequency dielectric response, the high frequency gold response, and yet we get an okay estimate.
Right, and the reason, that's right, and the reason for that is we could be, the insulator will actually also have, it's a matter of which things you are going to excite by that, on this frequency scale. Okay, so on the scales that we are looking at, which is around, let's say, 500 nanometer, are you really exciting the electrons of the insulator? Or are you exciting the electrons of the metal? So we are making that separation. Okay, so let's think about the material. We have a dielectric, which is also made up of electrons. Most of them are bound very strongly. So until I hit a frequency which is basically the binding energy of that oscillator, I'm practically in the 0 frequency limit of the dielectric. And on the other hand, the metal has these free electrons. So the moment I apply any electric field, it will start sloshing back and forth and responding. So that's why the metal response is much faster, and we can consider that. Now we have to be careful. If you start really exciting some of these core levels, which was giving me these big peaks in the dielectric function, then I have to worry about it. So what I'm saying here is, I'm putting an electric field with a certain frequency, and let's look at the modes that are oscillating. And at that frequency of 500 nanometers, it is really the metal. So I can treat the other stuff as static. Yeah. So we have to be careful about these things because tomorrow you change the material and everything changes. Again, you're playing the same games. So that's the story till here. And now so what we have seen is we started out with a gold plasma frequency of the bulk, which was way in the ultraviolet. And by putting in the size effect and the dielectric effect, it has come into the visible range, and not quite at 500 nanometers, but at 600. And the rest of it, I'm not getting into more details. What is missing is the fact that gold also has a dielectric constant correction because of the interband transitions. And so I'm going to show you some real data there, because at some level, while we can understand the color of the dot through surface plasmons, we cannot understand the color of gold. You might say, well, okay, this is all very nice. I'm getting a sense of the color of the nano dot. It has come up to 600, which is practically yellow, or slightly higher lambda, which is slightly lower frequency. But what about gold itself? How does gold get its color? And that, we found a plasma frequency of 9 eV. That's way ultraviolet. So it doesn't have that yellow color at all. So that's where, even for gold, we have to understand interband transitions. So we'll next talk about that. Let's see.
I'm not even sure I understand the connection between the absorption and the color. So we're saying it's absorbing at 600 nanometers, it looks red.
Okay.
That seems backwards. Or even if we just say
it's what is it's the
opposite.
It's
right?
the opposite.
But
yeah.
absorbing in the yellow
Yeah.
doesn't make something red.
Right. So what you want to look at really is the reflectivity. Okay. You want to look at the reflectivity and see where is the reflectivity high. What frequency is the reflectivity high? So let's look at that for just gold. I think I need to put this because now I want to show you some data. Okay, but I did promise myself I will not go between things. So let's wait a bit on that. But the next thing that I will show you is how to understand the color of just pure gold by including this one ingredient which we have left out, coming from so gold is not just an ordinary S-band material, it has D shells, and how does that play an important role? So we will do that. But I want to say a few other things that relate from this to some important developments in nanodots. Okay. So, how many of you know what Raman scattering is? Yeah? What is it?
I'm shining a laser at something and I'm measuring the shift in the frequencies due to vibrations of the molecules.
Yes. So you shine laser. Of course, when Raman did it, he looked at sunlight or some very poor source. It was literally, I should try to show you his paper. I was amazed. It's a one-page Nature paper for which he got the Nobel Prize. I have to check this with somebody more knowledgeable. But it seems there's just this one page, one single page where he just says he looked at sunlight and he saw these shifts, and I couldn't find any data there. And maybe there are follow-up papers, but it was literally this one page where he has, based on which he, I think, got the Nobel Prize for this effect. But it is exactly that. It is light. You shine light. So it's so here's your sample. You shine light, and you look at the shift. So you have some h nu, right? And you get a shift. H nu prime. You look at a frequency shift, right?
We look at inverse. We look at the wave. We look at the wave membership.
Yeah, okay. This is the HC over lambda. So let's say you get some H mu prime.
Machine isn't chemistry.
Is it in the chemistry building?
Yeah.
Ah, I knew it.
Right. So it's basically inelastic. It's inelastic light scattering. So that's what it is. It's a very important tool. Where have you seen it being used? What are the things it can be used for? You said something about molecule vibrations.
I use it to differentiate between the phases of carbon. So the different bonds, like sp2 and sp3.
Okay, so molecule vibrations. What else can we use it for?
I saw a talk one time with somebody who works in the Louvre, and they use Raman scattering to determine the composition of things in paintings, and they can determine where it was made or if it's been painted over. It's really interesting talk.
So sleuthing.
Yeah.
Yeah. Basically,
For
again,
art, because it was
art
non-destructive.
sleuthing,
Yeah.
right? Non-destructive art sleuthing, very important. So essentially, again, seeing molecules. What else?
You can use it to identify like graphene, so like single layer, double layer, 2 layers, multiple layers, and they'll show different raw motions.
Right. So basically, you can probe it. So going back to what we saw last quarter, where
Phonon spectra?
phonon spectra, but only close to, so let's see, it can also be used to see optical phonon spectra. Mainly because here's omega, here's Q.
Sure.
You remember we got things like this when we had basis atoms. That's where your layers come in. Suppose you have 2 graphene sheets and they are vibrating in phase, that's an in-phase mode. If they are vibrating out of phase, that's an optic mode. So Raman is very good for the optic modes around because, as you know, light has a very small wave vector. We calculated that for light. So it's essentially probing things around small q. So it probes Q approximately 0. So momentum transfer to the crystal is close to 0, and it's basically probing this optical, these things, the optical modes. There is an analogous inelastic light scattering to see acoustic modes, and that's called Brillouin scattering. It's not as common, but this is the one where you use inelastic light scattering to probe optical modes is more common. So this, of course, now I want to show you how this is its incarnation in the quantum dot case. Okay, how does this shape up when you now have something like a quantum dot? So now I want to get to what is called a new technique, very powerful technique called surface enhanced Raman spectroscopy. And so what is done is, we just looked at the plasma oscillations of a sphere, but you can make these things very, needle-like. You can change the aspect ratio of the sphere. So you can go all the way from a sphere and you can change that aspect ratio. And so on. So here your B versus A is very different. So this is my major axis, this is my minor axis, A and B. And you can see that you all remember from your E&M class, when you have pointy objects, the electric fields are very concentrated at the tip, right? So we worked out the plasma oscillations of the sphere But if you make it more and more elongated, then the electric fields are going to, the surface plasmons are going to be modified depending on the shape of your metals, not sphere, but your metal object. So again, I don't want to get into detail, but except to say that you're going to get essentially, let me just write down electric field. Electric field is enhanced. And so what is now going to be, what people do is, I don't know, maybe you do that in your lab. We talked about scanning tunneling. So you can, at that time we were bringing a tip to tunnel into some system, but now you can bring the tip just to do inelastic light scattering. So you can use the tip to be like a very strong electric field probe of your molecular vibrations. And so here's the idea, that you have a system, you have some molecule sitting here, and you bring in a tip, and the electric field at the tip point is extremely enhanced because of this lightning rod effect. And that electric field now excites modes in your molecule. And you can get Raman signals. Previously, you just had a plane wave hitting the system. You could excite the modes, but at the amplitude was very small. Now you have a very strong electric field, and that can give signals which are 1,000,000 times more intense than ordinary Raman scattering. So you have a very large signal to noise ratio. So that's the main reason, the main way this is being used. And the other point is it's a scanning probe. Previously you had this light coming in, it would excite something, but you got a global response. Now you can excite things point by point, just using this very, lightning rod effect near a tip. So let me. Are you using this, Curtis? This method? Is anybody using this method? Any? No? I know that in Jay's lab, they are using this along with scanning tunneling.
So it's an AC tip field?
Yeah, it's an AC tip field. You can do it both ways. But AC, you get an even more sensitive response because now you have an electric field at some frequency. You can even make it resonant with, let's say you are probing another object. You can even make it resonant with the plasma frequency of that object, and you will get a huge absorption.
Right. So I guess I don't understand how it would work in the DC case. What are you doing?
No, you don't want to use this in the DC case. You really want to use it in it. So think of our metal sphere in some dielectric. You could actually bring the tip and excite a plasma mode on one dot, and then nothing in the dielectric, and then move it to another dot, and so on. So the idea would be to do it in an inhomogeneous situation where you're mapping out the different metallic puddles or whatever, different molecules. Okay, so the main thing I want to just write down is that the Raman spectrum, so Raman intensity is about 1,000,000 times higher. And that is what allows you then to do local imaging. Because otherwise you're relying on many, many molecules giving you that factor of 1,000,000. Because you have a certain detecting capability. And unless you have a signal of that amount, you can't detect. So previously you were relying on 1,000,000 atom worth of material giving you that much enhancement. Now, because the signal has become 1,000,000 times higher, you can go down that much in the volume that is responding. Okay, so that is then this one neat technique. So what I want to do through these different aspects of quantum dots is bring also to your attention new techniques that are being used. So this is one of them. We've talked about tunneling, but this is now, so do Raman scattering. So this is let me write down one last thing. Raman scattering in conjunction with scanning tunneling. So the scan aspect is also there. And that gives information about local excitations.
So there's still a laser involved?
Yeah. Because the light has to come from a laser. And oftentimes what is done is the light is put through an optical fiber. So you have an optical fiber through which the light is coming in, and through the same optical fiber, you can collect the light and analyze it. So there are all kinds of different arrangements people can make. So that other technique which I was going to bring up later, near field scanning optical microscopy, that's another similar thing where you can look at an optic fiber to probe the local effect. And a carbon nanotube is another way to do this, where the carbon nanotube itself is the tip that is being used to probe the different surfaces. Yeah, question?
Yeah, so I've come across this once or twice, but they talked about depositing silver on the surface for the surface enhancer on spectroscopy. What did that have to do with it?
Yeah, so it's this thing that, if you have, what you want to do is, the metal sphere is playing a very important role. It's not a sphere. The metal, you make the metal, so the silver which is deposited, if you make it little pointy, okay, so here's one possibility, and this is something you should actually, this is something you should check with Jay a little bit, because as a theorist I can only step that much. I don't know all the details, but here's the point, that if you say shine laser on this metal sphere or metal dot, and it has and you shine it at a frequency which is resonant with the dot, okay, then you excite the dot at the resonant frequency of the plasma oscillation. So this one has plasma oscillations. Plasma frequency, let's say some new surface plasma. So the laser, this is the laser, it excites the metal sphere at that frequency. And its electric field is now greatly concentrated. It's like, my electric field arrows are now very concentrated here. And this is now coupling to some molecule. Okay, so that's kind of the idea, that you want to, the signal is enhanced. The laser has some intensity, and it has some electric field. Of course, overall, you're not violating any energy conservation. It's just that all of that electric field is concentrated at some point. So the metal sphere is used for the following reason. It's used to excite these surface plasmons. That's one reason. And then the shape is controlled to make it lightning rod-like, to concentrate the electric field. So with that then, the input becomes very intense. So this is an intense source of electric field. Okay? That's the 10 to the 6 enhancement of the initial electric field. Then it goes and couples to the vibrational modes of the molecule, and then you can see the shifts and read off those shifts from there. Yeah, that's
If you rotated the silver particle, would you have a different plasma frequency?
Yes, yes. So it's very dependent on the shape. If you make it like this, and now the way to think about it is the electric field. So, you have an electric field which is, let's say this is my incoming wave. And so the electric field is going to basically, in this, you're going to separate out the charges plus and minus, in this case over this scale, But here you're going to separate it out over this elongated scale. It's what is called the depolarization effect. And so that is very shape dependent. It comes in for magnetization as well. You know, whenever the system responds, the particular shape will change the magnetization response. So yes. Now, you know, if they can control it, so if you have just a suspension, you can't control how this shape will line up. So you might have to do some other tricks to line up the dipoles, not dipoles, but these sort of pneumatic metal objects. You know, you might have to do something to line them up, but here it's just a single one that they are targeting. Okay? Any other questions? No? Okay, so next what I want to do is this interband transition is indeed something I will have to do, but again, yeah, I think we could move to that, and then I have to think, do I not need the board at all? Okay, I will try to use the board minimally.
You want to turn this on?
Yeah, please.
It always takes 3 tries to plug in something. It's like one symmetry. It's like a USB port.
Yeah.
You have it right the first time, but it doesn't go.
Yeah.
So you flip it,
Yeah,
and
exactly.
it's wrong, and then you get it right on the 3rd time.
That's true. I'm just grateful every time I find my connector. It's like, okay, it's there.
What's the?
What are you looking for?
Okay, before this actually, let me show you that metal dots data. So I guess the other thing I wanted to say is, you know, it's like you'll see this in the literature. They will say the red color is due to tiny gold particles embedded in the glass which have an absorption peak around 520 nanometers. Statement. And so that's, you know, you can see how long it has taken us to unearth that statement. And that's kind of what I wanted to get some flavor for that. That, you know, these statements, there is a lot of physics and math behind it, but, you know, we had to go through all of these understanding of epsilon of omega, etc., the shape, the dielectric, etc. So I showed you this already, but it has gold and silver as well, and I'm trying to keep it simple, but here is the result. This is some, you know, now nobody defines what we have calculated. This is extinction coefficient, which is related to those epsilon and so on that we talked about. It was essentially related to the imaginary part of the absorption. You're trying to see over what length scale is the electric field getting extinguished by 1 over E of its original. But in any case, this is the calculation by David Stroud, I believe, and his collaborators, and the experiment is this dark line here. And, you know, it sort of gives you some absorption after putting in all of these multitude of effects. And what I found is, you know, the paper is very hard to penetrate, because what people do in these calculations is they will show you everything and say, here's the best fit. And actually, the best understanding you get is by doing it in steps. And that's another thing I want to communicate to you when you are doing research. Always do simple things and see where you are getting. So the kind of calculation I did is very valuable and very instructive. You are just doing a plasma calculation, and you say, okay, it gets me this far, not all the way. The reason is, if you take like the complete dielectric function, put it into some equation, chug and, just chug it out, okay, it will agree, but what have you learned? So it's very important to do it in steps, and that's basically how I think about it. Okay, now this shows now a different, it's too much detail, but I just want to tell you this kind of stuff exists, where they have taken on the left side experimental data for gold now in different shapes. Not just spheres, but oblate, etc., with different aspect ratios. And the right side is theory, again with different aspect ratios. And so you can look at this in more detail, and there's a caption which says that, what were the aspect ratios. But what I'm saying is people can now do these calculations and test some of it. And again, remember, this is only valid till you are in a regime that the wavelength is larger than the size of the dot, which is very well obeyed here. Okay, now let's look at something like this. This is good old aluminum. Okay, you look at aluminum, and if you look at its reflectivity, remember 2.5 EV was yellow. Okay, so what you see is its reflectivity is coming down from 1, and when you hit an energy scale, which is okay, so here I have plotted Eric's results for the reflectivity of a free electron gas. And what you see is it comes down from 1, then there's a plateau, and then there's another thing. It's all very featureless. Okay? Were you only looking at the free electrons in the S and the P band, or in one of the bands, this is the result you would have gotten. And I want you to contrast that with this. So you see a very sharp feature here where the reflectivity goes very small. I mean, relatively, it's still about 85%, but there's a big drop from what it was at low frequencies. And it's a very sharp feature, so it has to be associated with some very sharp transitions. And it turns out to be that there are 2 bands in aluminum, and you get excitations across that band. So one of the bands, this thing doesn't seem to work, yeah. One of the bands is filled, the other one is empty, and they seem to be parallel bands, okay? And I want to tell you the importance of that. When you have parallel bands, that tells you that at this value of the energy, there are many, many K points all along the band where the system will absorb. So you have a very high density of states for that particular energy. Everybody with me? The density of states is telling you what is the probability of absorption. You could have had, the 2 bands need not have been parallel. Each one could have had its own dispersion. In that case, you will have only 1 K point at which the energy will be equal to, let's say, a particular value, 2.5 eV. There will be only 1 K point where you will get a connection. But because these are parallel, you get a whole set of K points where you can connect the empty and the occupied band. And that gives you a huge enhancement in the density of states and a huge enhancement in absorption. And that's the cause of this dip. Question?
It seems like you could always just excite like a hotter electron.
Which could then fall down?
Yeah, exactly. So I'm a little confused by the statement that like the energy gap has to be.
There's an onset. Okay, so the point, yes.
Okay.
So you're right. Yeah, there's an onset, and then beyond that you can start exciting.
Okay.
But here, just because of this parallel bands, there's a huge onset.
Right.
At that particular, yeah, very good point. That, so Andy's point is once you have an energy more than the gap, you can excite many levels. And that is also happening. But in addition, at that particular energy, you get a big enhancement because of the density of states. Okay. This is now sodium. Again, we think of it as a free electron metal. But again, you see, now we have again these results for the free electron gas. This is the Drude conductivity. So that is shown here. At low frequencies, you are looking at sodium, which is an S-band metal, 3s, right? So you're just making excitations in the 3s band. And that's this particular behavior here. This is the Drude conductivity coming down. And it should have just come down and gone to 0, like this, all the way down. Instead, you see at another characteristic frequency right here, you get this big bump, enhanced absorption. And again, that is happening because of interband transition in sodium as well. So here it is. So this is, it's sodium, the Fermi energy is here. This is the band, S band. The Fermi energy is here. So when the frequency is less than this band gap, this is horrible. When the energy is less than this band gap, you're only exciting electrons or carriers around here. And that's the Drude part. And then when you make a transition across this, that's when you start to excite interband transitions. With me? Any questions? Okay, so like this, there are many other examples. Let's come to gold. And I couldn't find gold, but silver is just as good. Now, you know, this is the other thing. When you're trying to find literature, and I want to show just the same thing, reflectivity for everything, I can't find that. Somebody will quote epsilon, somebody will quote sigma, it's like all over the map. And that's why it's very good to have your presentations, you know, where you've taken at least the free electron thing for every single quantity, and you can, no matter what people throw at you, you can compare that quantity. So I want you to update your slides by tomorrow and bring that. And again, coming back now to epsilon 2, remember, epsilon 1 was the dielectric function, epsilon, and that was basically telling you about the polarization which was in phase. Epsilon 2 was the absorption. And again, you see, for silver, this is just the bare response here, but then at a particular frequency, around 4 electron volts, there is this big sharp feature in the absorption. And you can track it down, again, to particular, so here's the band structure, you know, all of that spaghetti. What is shown below is quite instructive. So this is just the free electron band, you know, epsilon going like k square, but, and we think of it as a parabola, but plotted in this particular Bravais lattice of gold. So gold has an FCC lattice, it has some Brillouin zone here, and if I plot along particular, this is all seems to have switched, but you know, not that it matters. You know, you can plot the band. This is the free electron band. This is the actual band structure of gold or silver. Looks very similar. But what I want to point out are these other bands here, which are not dispersing very much. You know what that word means. It means as a function of momentum, they're not kind of blowing up like this. That's called dispersion. They are very flat, which means they're very atomic-like. So these are the D bands. And the density of states, right? So density of states, obviously if I have a lot of bands in a narrow energy, that means the number of states per unit energy will be very large because it's a density. And so you can see that the density of states for S band is basically going like that square root of E which we derived. Okay, it's a very shallow square root of E. Whereas D bands are existing in a very narrow window and have a lot of structure. So this is the structure which then gets picked up in the interband transition, because the interband transition happens, this is the Fermi energy here, happens from these D bands to the S band. Okay. And that's, and you can read off those energies. They are indeed around 2 eV or 4 eV for silver, copper, gold, etc. And that's what gives the very special color. So that's the end of interband transition. Any questions?
So you get this peak in absorption due to an interband transition, but it seems like the shape of the absorption around that peak also needs to be taken into account to get the actual color, right? Because you said that you have to kind of take the inverse of the absorption to get the color of the
Right,
actual.
so what you should be doing is ultimately looking at reflectivity. This is the quantity you want to look at.
Right.
So, you know, you have to see where is the reflectivity high. So, what I mean by take the inverse is, you know, if you measure epsilon 2, which is absorption, then you have to run it through the square root of epsilon and get n and then feed it into this.
Right.
And that's what will tell you then what the reflectance is.
Right.
So typically there's absorption at some frequency. Yeah, so let's say there's absorption at a particular frequency, omega naught. So in epsilon 2, that is where there was a peak. If you go back and look at reflectivity, you would see a depletion at that.
Mm-hmm.
And so you would say, well, you know, reflective, this light got absorbed. So basically it's so whatever is the complementary color, if something is yellow, the complementary color of yellow got absorbed, hence we are seeing yellow. Yeah.
Okay.
Is that clear?
Yeah, I guess so.
I think the best way to see that is to make a little model with a very sharp absorption, and we have that model. I actually did that for the insulator with some characteristic frequency omega naught. Okay, so we have that expression for epsilon of omega which absorbs at omega naught, and I gave you that long expression. What we need to do is just run that through and get the reflectivity, and that will then tell us how does that omega naught scale show up in reflectivity.
Mm-hmm.
This could be your project if you want to do that. You can think about it.
Okay.
Okay, so that's the story here. Now I wanted to bring up nanodots again in this context. Okay, in everything what I'm trying to do is kind of cover a little bit of basic stuff, but then show you where nanodots is taking this idea. So it's actually very interesting, and the way it comes up is, again I need to use the board, but okay,
All right, is this a PowerPoint?
yeah,
Just hit B on your keyboard and,
B.
yeah, the letter B, and now put the screen up.
Ah, that's fantastic. So, let's see. So now you might ask, what happens to absorption in a quantum dot? And there are two effects. One is what we know. Okay, a quantum dot, all the levels get discrete. That part we have already discussed. But the other part is also interesting, that if I take a macro, this is macro, this is, let's say, meso, and this is our quantum dot. And I just try to draw the conduction and valence bands in all of these three situations. Here, this is my valence band, very dense set of states. I come to the mesoscale, they are starting to become discrete, but the other thing is that because of confinement, the band gap also gets pushed to a bigger value. Okay, so this is increasing. So here is the this is E gap, bulk, meso, and then in the quantum dot, the discreteness has gone up, and this for example, in zinc sulfide, it has a gap of bulk, which is about 3.6 eV, and E gap quantum dot about 1 to 4 nanometers. It's about 4.5 eV. Okay, so that gives you a very good window into like engineering absorption spectra in the regime you want. So depending on how you want this, you can use different dots. And one of the applications is to use this to target in a biological material. You can use this to luminesce at different energy scales. And the main excitation that one generates, so let's say everything, here's my chemical potential, everything below the chemical potential is filled, everything above is empty. I make an excitation, I make a hole here and put an electron here. And this object is called an exciton. Okay, these are, what do I mean by an exciton? You might say, oh, I just put an electron there, it should be running around in plane wave states. But there is a small attraction between the hole and the electron, and that generates a bound pair, like your hydrogenic atom. Now this happens, what I want to stress is this happens even in ordinary semiconductors. But the wave functions involved are plane wave states. So you construct this exciton, a bound state, out of plane wave states. So the binding energy is much smaller than in the dot. So that's the reason they are very dominant, because once you have a dot, you already have a cutoff on the size of the exciton. It can't go flying anywhere. It's confined in the dot. And that makes it more localized as opposed to an exciton in the bulk. Is that clear? Okay. So let's just write this down. So an exciton is a bound electron hole, and its binding energy, basically the radius, A exciton, is going to be h bar square over m star. Remember, all masses become effective masses. This is just like our silicon doped with phosphorus calculation. M star, so 1 over m star is essentially 1 over m electron plus 1 over m hole. Okay, so that's the m star, and then we have E square over epsilon. I'll put an epsilon naught. It's the dielectric function of the semiconductor, of the quantum dot.
This is kind of a different m star, right? Because before the effective mass was because of band curvature, and here we're just calling it like a reduced mass.
It is a reduced
this
mass.
system.
It is a reduced mass. So this is really, so what each of these, okay, each of these ME and MH is the effective mass due to the band curvature. Okay, because what I have is, let's say in gallium arsenide I have something like this. So each of these masses, and you have to worry about light hole, heavy hole, we're not even going into that. But basically each of these would be effective band masses.
But do we still have that in a quantum dot?
Yeah, okay, so that itself is an interesting question. You have to, you will still have, you can still, so this mass just becomes now a second derivative of your eigenvalue in some basis. Okay, but it actually has to be questioned. This entire picture of effective masses and everything has to be questioned. So yes, there is, that's something I'm not going into, but that's like an effect, you're kind of assuming that your electron waves are able to travel over large distances when you define these effective masses. So it does have to be revisited. You have to basically solve the entire structure of eigenvalues for the dot. But let's say if you had to pick something, this is what it would be, and now m star is the reduced mass of this duo. Right? You go into the center of mass coordinate, relative, etc., and then this is the reduced mass. And then here's the dielectric function. Again, you can worry it's a quantum dot, on the scale. What are you calling a dielectric function? All these things need to be revisited, but you end up getting this. Okay? So for typical values of epsilon naught and masses and so on, this ends up being a very large scale. Why don't I have that scale here? Okay, we can just do it here. Epsilon is about 10. Mass is about 0.1, let's say, so it's about 100 times A naught.
What is the m in the numerator there?
Oh, sorry, this is M0. This is the mass of electron, just the free electronic mass, because I made this the Bohr atom. That's the Bohr radius. Okay, so that's the free electron mass. Yeah? Okay? So this is mass of. Okay, so it's about 100 A naught. So it's a big object. Okay, this exciton, think about it. It's a semiconductor dot, or even a bulk semiconductor. You have excited an electron-hole pair, but it's a big object, and it has a binding energy which is also finite, and this is called an exciton. And at some point, this electron and hole can recombine and emit light, and that is called photoluminescence. So people can detect the signal, and from that they can look at the binding energy of such an exciton. And these are the main excitations of a quantum dot. Okay? So when we talk about quantum dots, in the case of semiconductors, we didn't fixate on this too much because we were just looking at excitations across the gap. The excitation energy of an exciton was very small. It renormalized things, but it was a smaller renormalization. Here, this turns out to be the dominant excitation because everything is discrete. So you make such an excitation, this is a delocalized object but bound, and at some point it recombines and emits light. So, so basically photoluminescence, which I won't spell again, it's spelled there, is the light emitted when electron and hole recombine. And this is quite a powerful technique. You can also just think about using it to probe spin, because if the light is polarized, you can get spin information. So I won't go into that right now. Okay, let me just say one more thing. From this bound radius, you can also calculate a binding energy, E excitation, and that will turn out to be 13.6 eV. Times something or the other, m star over n, 1 over epsilon square. So the main point about this is that you will get absorption or emission below the band gap. Okay, so suppose I was just looking at excitations even in the bulk semiconductor. You have a band gap, but because you have a bound state, an exciton bound state, that means you have a state available below the gap by this much. This is the binding energy. So here is the valence band, conduction band, and this is there's some excitation energy, which is, it can be anywhere in the gap. And this difference is Ex. Okay, so the main point about an exciton is that you will get absorption in a semiconductor or in a quantum dot, which is below what you would have calculated to be the gap. So in this case, you may have calculated, this is my highest, what is it called? Lumo homo, highest occupied. Lowest unoccupied, highest occupied, molecular orbital. Okay, so you can calculate these things and you'll say, okay, this is my gap. But if you do an absorption study, you will find that you'll get absorption at a slightly lower or at a lower energy given by this exciton effect. Let's see quickly. 2 minutes, yeah.
Question, wouldn't this usually be pretty small because it's like the binding energy of the exciton, right?
Except in quantum dots, it can become quite large because you're now confining them. So, yeah.
So we said in this picture over here that the difference between the HOMO and the LUMO is bigger than E gap in the bulk.
Yes.
So is this a
this
correction to which picture? I guess?
So this is now, when I say this, what I mean is,
That picture.
this is now, so yeah, let me draw it in both pictures. In both pictures you can get this. So in this case you would get, this would be, so this would be my LUMO, HOMO, and then this is the E exciton. And here also there will be a much smaller, you know, this would be much smaller, but there will be E exciton here. And this will be the conduction valence. Okay, so the main point in the dot is that you can shift this exciton by a lot more. Okay. So Andy, what was the magic thing now to get it back?
Just hit B again.
Just hit B again. So that is just dots with, you know, beautiful cadmium selenide is a very important dot material which, you know, by changing the size, now this is not excitonic, this is just across the HOMO-LUMO gap. Okay, one can get different colors. I'm going to get to excitons in a bit. There's a nice paper here. This one. Okay, it's again, you know, it's amazing where people are taking this field. My respect for some of these things has grown as I'm learning more about it. But this is now an optical dot where using a new technique called near field scanning optical microscopy. And we can't go into this except what is amazing about it is if you use light, okay, this is what we all learn. If you use light with a wavelength lambda, you can see features of order lambda, right? You can't see smaller features because it's diffraction limited. Well, turns out if you're in the near field of this light, you can image much smaller features. Okay, this is something I don't understand very well, but it's becoming very crucial for a lot of imaging things today. Near field, where you break the diffraction limit. I mean, you go beyond, you can see distances smaller than what you might have considered to be a limit. And using that, they can, so here they use an optical fiber and then they excite in the gallium arsenide region, in that little quantum dot, they make such an excitation. They excite such an excitation, electron-hole pair, and then a lot of details. It's a Physics Today article, so you can read it. And then they can image the actual wave function of this excitation, because the intensity, not the wave function, but the wave function square. Okay, so the wave function square is a function of the center of mass coordinate of the exciton. Okay, so the exciton are these two objects. You can write it in terms of the relative and the center of mass. And so by center of mass, I mean that the exciton is sitting in some part of that semiconducting dot. And by looking at the intensity from different points, they can map out the wave function square, or the probability of finding that excitation. And there it is. It's a pretty amazing experiment. And you know, then they can look at what is the energy, what is the size, you know, what have you. You don't have to rely on any calculations or imagination, and there it is. Okay, and then the last thing, I have to stop now, but the last thing I want to show you is just the title, and then you can read more about it. But this is now, again, quantum dots, which are being used for biological imaging. So what they do is, and it's a whole lot of detail here, but basically they can attach all kinds of proteins on these dots and then send them into the cell, and they can play around with, because they can play around with the frequency, they can get it in a regime where, let's say it's in the infrared regime. So, the cells, if they are hotter or colder, they will image that at the infrared regime, and they can get pictures like this. So, this is some cell, it had some tumor, it all sounds very exciting, you can bring in a nice biological application. So there's some tumor somewhere. So here's the quantum dot with all these proteins, and then it can go and tell you, okay, this is the size of the tumor, because the tumor is maybe hotter for some reason, it has more metabolic activity. I'm just making all this up, but there it is. So that kind of brings us to a close on all of this quantum dot stuff, and we have basically seen quite a lot about the insulating quantum dots, all of this nice Coulomb staircase and the metallic ones, and we have kind of discussed the optical and frequency dependent response in quite some detail. So next time, tomorrow, I know some of you told me you don't like these extra Wednesday classes. Never mind, we have a lot to learn, believe it or not. We really do have a lot to learn, so I'm going to have them. And if somebody doesn't like them and finds them impinging on your other schedule, you should feel free to not come. And that's your prerogative. But I'm going to have them because we cannot have so much discussion, and I cannot cover that much material. So it's important to have the discussions and meet more often. And we can make these interactions very different. Like Eric, how did you find that a tutorial that you all participated in? Was that useful? We can do more of these for those who want some. So what I'm going to do next time is I'm going to bring in spin, because that's another very important angle in these dots. And it's a very nice connection. You make things into dots, you enhance the Coulomb repulsion, you bring in spin, you expose the spin of the electron. And then from there, there's a very direct flow of tunneling, transport, everything involving spin. So that will be our topic for the next some lectures. Okay?
Still in this room?
Yeah, all of it in this room. Yeah, we move.